we learned about what exactly is the electric potential, that is the potential in the vicinity of a particular charge. Now, if we bring any other charge close to it from, let's say, infinity to a point, obviously we'll be doing some work, right? How much is the work that is stored in it? That is going to be in the form of a potential energy. Let's try to learn about potential energy.
So let's try to understand about what exactly is the potential energy difference. We have understood about the electric potential at a particular point. So let's try to briefly go over as to what exactly does potential energy difference stand for. So when we talk about the potential energy difference, let's say here we have a particular point and we are moving on. So this is a particular point and you have at this particular point A, you have another charge. So there is going to be a potential energy stored between these two. Means when you are either trying to bring it together, there is going to be force of repulsion. If you are trying to take it away, there is going to be kind of a pseudo force of attraction. So this results into a kind of potential energy difference. So when we talk about the electric potential and the potential energy difference, what exactly does that stand for? Let's try to understand. Supposing you have a positive stress charge Q naught, which supposing it is moving by a displacement ds from an equipotential surface to any other adjacent surface. So therefore the potential difference is there. In this case, since it is along the same line of electric field, there is not going to be any change in electric field, but there is going to be a change in electric potential, right? Moving on from there, what we say in this case, the work done by the electric field is going to be defined as negative du, as we just understood some time back. So this is going to be given by Q naught into dV. So this is the relation between work done and the potential difference. Here Q naught is nothing but the test charge. But V can be represented as E into ds. dV can be represented minus of E into ds. Therefore, work done is represented in terms of electric field and the displacement in such a way. So now, if I say that the electric field is directed like, or let's say my charge is moving in this direction, but my electric field is directed like this. There is an angle between them, right? So the work done is going to be maximum when we take the component of the electric field. So if I take, this is the direction of ds and this is the direction of electric field. So you need to take the component of ds along the electric field or vice versa. So when we take the component, because work done being a scalar quantity, it should not be dependent upon the direction at all. So the work done is going to be just the scalar component of the electric field along ds or ds along the electric field. So that gives us, so that tells us that the component of electric field, if I am taking it, so that is going to be given by something like dV by ds. Therefore, if I individually want to find out what is the electric field component, because electric field is a vector quantity, so this is going to be given by partial derivative. This is not a complete derivative. You are only going to find out the variation in the potential along x-axis, along y-axis and along z-axis. These are going to give you the three different values of electric field, Ex, Ey, Ez. So these are the three different directions of the electric field. These are the three different values of electric field that we are going to get. Now, let's try to understand it with the help of a numerical. First numerical goes as this. So you have to calculate the potential at a point P due to a charge this. It's very simple, located 9 centimeters away. So what you are going to do? You're just going to put in the values Q, R, 4 pi epsilon naught. You know that 1 over 4 pi epsilon naught is nothing but 9 to 10 raised to the power 9. Charge is given as 2 into 10 raised to the power minus 7. The distance is given as 9 centimeters, so it comes out to be 0.09. Putting it all together gives you very simply this. So 2 into 10 raised to the power 4 volts it is. Now this is the potential, mind you, and therefore if you are required to find out, this is how much. So this is the potential that you get. Therefore from here you can find out how much is the work that is done. The work done is nothing but Q into V. The value of Q is given to you, the value of V is given to you. So this on finding out is going to give you, so there is a minus sign that should have been placed here. So this is the amount of work that we get. But this was very simple. Let's move on to the next one. So what we have here, it says a spherical conductor of radius 12 centimeters and having a charge 1.6 is distributed uniformly. Yeah. So what is the electric field inside the sphere, just outside the sphere, and at a point 80 centimeters from the center of the sphere. So when we are talking about 18 centimeters, effectively it means that it is going out, right? So when we talk about the electric field, what is the expression of the electric field that we have? The expression of the electric field goes as 1 over 4 pi epsilon naught. You have Q over R square. So this is nothing but 9 into 10 raised to the power 9 into the Q over R square. So this is going to be the next general expression. So when we are talking about inside the sphere, charge is only going to be distributed on the sphere. It's distributed on the surface, and therefore the electric field inside the surface of the sphere is going to be 0, right? Because it's going to be an equipotential surface. So on this equipotential surface, there is not going to, within this equipotential surface, there is not going to be any value of electric field. So inside the sphere, it's going to be 0. Now if we move on to the part B, just outside the sphere. Just outside means you can take the radius to be 12 centimeters, right? So let's move on there. So yeah. So just outside the sphere, if I have it, so it becomes 9 into 10 raised to the power 9. The charge is given as 1.6 into 10 raised to the power minus 7. The distance is going to be distance squared, so 12 centimeters it is, so it's going to be 0.12 whole square. This is just outside. Okay, then at a distance of 18. So when you are at a distance of 18, obviously you are outside this particular sphere. Yeah, so that means here what will you get? You get E18. That's going to be equals to 9 into 10 raised to the power 9 into 1.6 into 10 raised to the power minus 7. These things remain as is. It's not going to be any change. Here only you are going to get a difference, as it should be 0.18 square. That's it. That's nothing other difference. No other difference that's going to come up here. Hopefully it's clear, right? Okay, so hopefully you understood whatever we discussed out here. This potential would have enlightened you slightly. We'll discuss further more problems as well. So stay tuned, we'll move on.
So students, we learned about what exactly is the potential energy. When you bring a charge from infinity to a particular point, you need some external agency to do the work. That work, in a way, is stored in the form of potential energy within the system, right? So we need to understand as to what exactly is the relation between potential energy and the potential at a particular point, because the potential is going to influence as to how much is the work that needs to be stored when you bring a charge from infinity. Let's try to take this further and try to understand about what exactly is the potential energy of a dipole. So stay tuned for that.